Alright, so thus far, we've just been focusing on how to use the definitions of derivatives to come up with the derivative of a function at a point, or a derivative, um, or the general equation for the derivative of a function. But, I mean, I don't know about you guys, but having to simplify like this equation limit as h tends to 0, f of x plus h minus f of x divided by h for every like function f. It's pretty tedious, right? But luckily, um, we have this thing called rules of differentiation, and it basically means for certain classes of functions there's similar patterns of how this equation simplifies to, and so we don't have to always use this equation to find the equation for the derivative of a function. Instead, we can just use our rules. So let's just get started with the rules. So the first one is derivative of a constant function. Okay. So let's just say there's like a function f of x which always takes on the value of c. So the derivative of f with respect to x, so notice the notation is, and we can write it similar to this where we're just substituting in c, is always equal to 0. And the proof of that is pretty simple. So for all the proofs of derivatives, we just use this equation. So it's really not too difficult, but knowing how to prove it once, it's probably helpful in seeing where we got these equations from. So we know limit as h tends to 0, f of x plus h divided by h minus f of x. That gives us the derivative of a function. And we know that f of x plus h is always c, and similarly, f of x is always c. So limit as h tends to 0, and that's just equal to the limit as h tends to 0 of 0, so then we get 0. Okay, so that's the derivative of a constant function. Let's move on. Okay, so our second type of common functions we'll see is the power rule. So power rule. So this works for any function which has like a powered function. So any function in the form of f of x is equal to x to the power of some n, right? So if we have this sort of function, the derivative of f with respect to x, this is just equal to n times x to the power of n minus 1. And then we'll have a proof over here. So proof is, okay, so proof of this one is it's a little more complicated, but we can still do it. So we know that limit as h tends to 0 of f of x plus h minus f of x divided by h will give us the derivative, and if we plug stuff in for x plus h, we'll get x plus h to the power of n minus x to the power of n divided by h. And basically, we know that we can simplify this through the difference rule, and that gives us x plus h minus x times x plus h to the power of n minus 1 plus x plus h to the power of n minus 2 times x, and then we keep going until we reach plus x to the power of n minus 1. Okay, so that's what our numerator will be if we factor this out. And our denominator is just h right here, And so notice how here we have x minus x, and so that cancels out. We will have h left, and that whole thing cancels out. And then we have limit. Notice we had limit as h tends to 0. And in the end, what we're going to get is we're going to get n terms. Each with limit x to the each with limit x to the power of n minus 1, because what's going to happen is, for example, limit as h tends to 0, right? If we plug in 0, what we will get like x to the we'll get x to the power of n minus 1 time plus x to the power of n minus 2 times x dot 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 plus x to the power of n minus 1, right? And then that just becomes n times x to the power of n minus 1. So then we get our final answer. So a little bit more complex, but luckily you probably don't have to remember the proof, and usually you're not going to be dealing with like an arbitrary n. But anywho, whenever we have a power function, the derivative of the power function is just taking the exponent, putting it in as the coefficient, and then reducing the exponent. So this is more important. Okay. So our next type of functions is the constant multiplication rule. So let's say we have a so the constant rule. So assume we have a differentiable function f, right? So the derivative, so d of c times f, so c is a constant, and then let c be a constant. Right? The derivative of c times f with respect to x is the same as c times the derivative of f with respect to x. And so the proof of this is so ddx of c times some function f is equal to limit as h tends to 0 of c times f of x plus h minus c times f of x, right? Because it's just the same function, but everything's multiplied by c divided by h, right? And so we can take the c out because we know our constant rules for limits, right? We can just take the c out for like this, and then we're just left with x plus h minus f of x over h. And we know that since f is a differentiable function, this part just simplifies to the derivative of f, right? So we'll just get c times f prime of x. And then basically what it's the same thing as what I claimed, that whenever we have a constant that's multiplied to a function, right, the derivative of that is just the derivative of the function itself times the constant. And so because like the constant can be like a fraction, right, this takes care of like if a function's divided to, right, because 1 over 2 times f of x, right, you can treat this as f of x divided by 2 or multiplying by the constant 1/2. So this takes care of both the cases. Okay, let's move on to the next one. Okay, so the sum and difference rule. So the fourth rule is sum and difference. Okay, so this just says the derivative with respect to x of like two functions, f plus or minus g, is equal to the derivative of f with respect to x plus or minus whatever the term is over here, the derivative of g with respect to x. So what it's saying is basically we can split up whenever we have like a function that comprises of two smaller functions in it, we can split those functions up, find the derivative of them individually, and then add it up together. And the proof of that is also not too difficult, so let me just go over it. Proof. So we have d dx of f of x plus g of x, right? And that's just the limit as h tends to 0 of f of x plus h plus g of x plus h, right? Because our functions just consist of, like, we're splitting the functions up, right? Minus f of x minus g of x divided by h. And then if we know from our fraction rules, what we can basically do is like take these two terms together and put them with this common denominator of h, and then take this term and this term together and put them under the common denominator of h. So we'll get something like this: f of x plus h minus f of x divided by h, and then we'll get plus f of g of x plus h minus g of x divided by h, right? And then we know that this is just the derivative of f, and this is just the derivative of g. And that's basically what I wrote over here. And then if we had a subtraction sign, right, instead of this plus over here, we would have a negative. And that's basically it. Okay, let's move on to the next one. So our next rule is, actually, before we move on to the next rule, I think I'll just split this video into multiple parts because there's a lot of different rules coming up. So let's just go through some examples, okay? Examples. Okay. So let's find the derivative. So find dp over dt, right? So we know that this notation just means the derivative of p with respect to t, right? So, and we're given, this is function p is t cubed plus 6t squared minus 5 over 3t plus 16, okay? So we want to find the derivative of p with respect to t, and we know that p is defined in terms of t, and so this is just finding the derivative of this function, right? So this looks pretty complex, but let's try to use the rules we have learned so far to make this easy and not have to apply this big, like our limit definition of derivatives, which let me write once again, right? Like, we know that applying this definition to this equation is going to be a huge pain, right? That's why we use the rules. Okay, so let me, on the left side, I'll write dp over dt, right? Okay, so notice that this function over here is the sum of smaller functions, right? So we can use our sum rule and just focus on each of these terms right here separately and find the derivative of that and either add or subtract. So let's look at the first term. This is a power rule. So t to the power of 3, right? Using the power rule, the derivative of that is just 3 times t squared, right? And then here, it's very similar. We have a powered function, but we have a constant in front of it, right? So that's just the same thing as having the constant, and then we apply the power rule, so taking down the 2, and then t to the 1, right? And then here, it's just a constant, right? And so and then this is another powered function, except this power is 1, right? But we kind of omit it. So it's pi over 3 times 1 times t to the 0. And we know t to the 0 is just 1. So later on, when we simplify, we just remove the t term. And then we know the derivative of the constant is just 0. So we'll get 0. And then for our final answer, when we clean it up, right, we'll get 3t squared plus 12t minus 5 over 3. And then I remove the t because t to the 0 is just 1. Right? So notice how I just use my power rule and my constant rules and my sum of different functions rules, sum and difference of them to find the final derivative. Okay. Now let's go on to another question, which is not as obvious that we have to use derivatives, but again, we're going to start seeing examples of why derivatives are so useful. So we have a function y is equal to x to the power of 4 minus 2x squared plus 2. And the question is, does this function have horizontal tangents? And then, if so, where? Okay. So, what does it mean to have a horizontal tangent, right? So, a horizontal tangent means our tangent line is like flat. And when we have a flat tangent line, essentially the slope of this tangent line is 0. So, slope equals 0. So, essentially what and we know that our tangent line, the slope of it is given through the derivative function. So, essentially what we're trying to do is we're trying to find the the areas where our slope is 0. Okay? And to do that, we first have to find the derivative. So y prime, and then to find the derivative of this, again, we split this into different smaller sections. So the derivative of x to the power 4 is just 4x cubed minus 4x, and then the derivative of this is minus 4x, and then this is 0. So our derivative is just 4x cubed minus 4x. And then we want to find where this is 0, because we want to find horizontal tangent lines. So when is y prime 0? So we just solve for that. So 4x cubed minus 4x. We factor. We get 4x, and then we take x squared common, and here we have 1. We can further factor this using the difference rule, difference to square rule, right? And then now, if we solve for 0, we get x is equal to 0, x is equal to 1, and x is equal to -1. So the answer is yes, and then it's at these points. So yes, and then at these points. Okay. So again, we see how like all the applications of derivatives still stand, right? Derivatives, what it means is where it describes the slope of the tangent line. And this question was asking, where does the function have horizontal tangent lines? So horizontal means our tangent line has a slope 0, so we automatically find first the derivative, which describes the slope of the tangent line at a random x, and then we find where that's 0 to find the horizontal tangent lines. Okay. And so that's kind of like the different applications. Like we can see how the rules of derivatives are pretty powerful, right? We don't have to use the limit definition to calculate these things anymore, and it really simplifies and speeds up our problem solving. There's many more functions, and they all have their different rules, and there's also stuff like product rule for like the product of two functions, and quotient rule, and I'll cover that later.